Welcome everybody back to the second day of the Gorman lectures. So Ariel has been introduced, so I'm here just to welcome you. So Ariel,
Thanks.
is yours.
We started on the second Gorman lecture last time. For those who weren't here, I don't know if there aren't, I'll give you like a 2-minute where we are. Hopefully that'll be enough. Basically, what we're trying to do is that the standard models used for dynamics and I/O have sort of two kinds of problems. One is basic cognitive. They require people to know too much and to make too many assumptions. To have too much information the information requirements are huge, and they have to be able to compute policies for a huge number of states, including states that they've never visited before. Okay, so to get around it in empirical I/O, one of the things people do are unilateral effects, which is that I see what happens when we do a policy to one firm, and we see what happens to that one firm, but we don't do the re-equilibrium. Or we do approximations, and the approximations are for the data that exists. And the counterfactual is a different data set. So the approximation is not the right approximation, okay? So theorists have done, I'm not going to go over this again, but theorists were well aware of this problem. And indeed, there was some empirical work that was well aware of this problem. And the way they proceeded was they used weaker notions of equilibrium that had less cognitive requirements. I'm going to take off my jacket. I don't know why I started with it in the first place. I knew I was going to take it off. So there was some applied work like this too. It was all in a situation where what the interest was, it was a repeated gain. So the idea was I have to learn how my competitors behave. Is that clear in order to do it? But the actual state variable, the payoff relevant variables in the system didn't evolve over time. Okay, so for empirical I/O, that's not a good starting point. Okay, so we're after the effect of investment strategies, R&D, advertising, physical investment, whatever you like. So what we did, this experience-based equilibrium, which is what I'm going to talk about today. First of all, I'm going to talk just about the theory and a learning theory that goes with it. And the second, I'm going to talk about an empirical project with Pierre, which is sitting right here, on how to implement it empirically. Okay, that's going to be the problem. So the experience-based equilibrium, all it really does is it takes these ideas from theory and it puts it into a model where you can invest in your payoff relevant random variables and they evolve over time. Okay, that was the whole goal. Okay. So the framework, the analytic framework, it has two parts. There's this notion of equilibrium, which is the first thing I'm going to tell you about. And then there's a learning theory that can get you to equilibrium. Okay. The equilibrium strategies are rest points to a dynamical system. So at each point, okay, we each are doing the best we can given what our competitors are doing, just like in standard Nash theory. So we're going to assume that firms perceive they are doing the best they can, okay, and that these perceptions are consistent with what they observe, okay. So maximizing behavior is maximizing behavior, only I'm not going to assume that the agents are correct in their perceptions, okay? And that's going to be true also in the empirical work. But there will be this, at the equilibrium at least, there's going to be partial consistency of these perceptions. What that means is if a state is visited repeatedly, I see the distribution of outcomes for my actions. Is that clear? Seeing I see the distribution of outcome from my actions, and I can estimate that consistently, I can optimize against that, okay? So provided the state is visited repeatedly, I'm going to do, well, at least I'm going to do the right thing, okay? Different agents can have different information sets, so there's asymmetric information. The theory doesn't constrain what's in them, okay? So I'm just going to give you a broad theory. That's the answer. It does reduce cognitive requirements because it's only on a reduced space that I have to get things correctly. the thing to note, is the theory is silent about what's in this information set, but the empirical work has to decide what's in this information set. You got to do something. Okay. I'm just going to formalize a little bit. There'll be a little bit of theory. I'm going to let the information set of firm I be denoted by JIT. So it's going to contain public information, which is, I guess, zeta T. So different, okay, I'm going to call it zeta T, okay? And private information, omega IT. So the information set is the sum of the two of them. The public information can differ across firms. It doesn't bother me. And it's used to predict competitive behavior. So I need to somehow predict what my competitors are going to do in response to me. Common demand and cost conditions, et cetera. So now what we have is we have an information set of each active agent, okay? So that's the state of the Markov process, J1T to JNTT. NT is the number of firms at T. So those are the information sets of the agents, okay? So that's the state space for the model. And it's going to be a finite Markov process. I'm going to take the simplest model. You can generalize this, and we have in other papers. I'm going to let policies, MIT, be just a finite set of policies. And they're going to be a function. I have to formulate a policy as a function of what I know. So it's a function of my state variables, okay? I'm going to assume the possible policies is finite. Actually, in the application, it won't be, but it's okay. And that it's what we call the capital accumulation game by most theorists. What's a capital accumulation game? My private state typically can evolve over time as a function of my control and my competitor's control, and where I am, where my private state is now. Is that clear? That could be a vector, it doesn't matter. Okay. What a capital accumulation game says is the evolution of my state, my private state, doesn't depend on the actions of my competitors. Okay. So if you were doing capital accumulation, investment, my capital last year gives me capital this year. Okay. But if you were doing an auction, okay, and you had, timber in you have a timber thing and you're auctioning for the next lot of timber, which is one of the auctions in America. How my stock of timber evolves depends not only on my bid, but also on my competitor's bid, because they can win when I'm not. So this is a very restrictive assumption, but it's easy. We've done it without this assumption. It's just, this makes it easy to tell you what's going on. Okay. So a state of the system is this vector of information sets, one for each agent, but the agent himself doesn't need to keep track of this whole set of states. The agent, he or she, whoever it is, it only needs to keep track of its own information set. Is that clear? Okay. So it's going to be a Markov process. And this is just standard Markov process theory. If it's a Markov process on a finite state space, it eventually has to move into a subset of the states and stay there forever. Okay, this is called the recurrent class. I could do this on the blackboard. It's just, in 2 dimensions, there's going to be lots of dimensions, but in 2 dimensions, you'd have states in some box, and wherever you are, you will eventually go into one of these recurrent classes. And once you're in it, you'll never leave with probability 1. That's got to be true of any Markov process. Okay. Okay. And in order to make a decision, each agent has to have a perception of the expected discounted value of the net cash flow from the different options available to it. So it's going to, remember, I'm assuming the agent's trying to maximize. So to maximize, I have to have a perception of what I would get if I take different actions. Okay. That perception consists of an expected profit. And the script E here is like, you'll see it again in the thing. That's my perceptions of the expected profits. They need not be correct. And a continuation value, which I'm going to call W. And I think this was the same notation that was used yesterday, if I've got it right. So somehow the notation is getting good. or at least I don't good, but it's getting common, which helps. Okay, so each agent's going to maximize its perception of its expected value. Remember, this is our equilibrium conditions now. And for those states that are visited repeatedly, these perceptions are consistent with observed outcomes. Those are the conditions. Formally, they're this. Take any M and M. So if M star is is what I choose to play, okay? And that JI, this M star, the perception of the continuation value from M star has got to be greater than M. Okay, than any M. Okay, and that perception, the perception of the value, that perception has got for points that are in the recurrent class that I visit infinitely often or many, many times. Okay, that perception has to equal the expected value of profits, where this expectation now is the empirical expectation, and I will define it in a second, okay? Plus the expected continuation value, where again, this is the empirical probability distribution, okay? So what is this? So pi e is just the expected profits. There is, when everybody's playing their equilibrium policies, okay, there is a distribution of j minus I given ji. Okay, so, and if I just keep track of the average, the profits, and average it out, that's what it's going to average out to. Okay, so these probabilities here are just the probability of j minus I and ji divided just like a normal conditional probability. Okay, similarly, the probabilities here are just the probability of j prime given ji divided by the probability, the empirical probability of ji. So it's just the empirical probability. That's why it's called experience-based equilibrium. Okay, so those are the equilibrium conditions. Okay, good. I want you to take note of a couple of things. First of all, it should be pretty clear that Markov perfect Bayesian will satisfy these conditions. So this is a special case of Markov perfect Bayes, okay, but it's one that I think is usable. I don't know how many here have been, I know the CMA here has, I don't know how many here are familiar with the algorithmic pricing literature. Okay, so this is the condition, this is also the condition for converged policies in that literature. It's exactly the same. Okay, the thing to notice about it, okay, and where the problems are going to arise, okay, for both the algorithmic pricing literature and for us, okay, is the continuation values are correct. Say we're in the recurrent class. Once we're in the recurrent class, we don't leave it. Okay? So say we're in the recurrent class. Okay? Whoops, did I do something? No, I didn't. Good. The continuation values are correct for the actual values that the agent chooses. Let me go back for a second. So the continuation values here, they're right for the actual value. I have that right. Okay? The profits are about right for any M. Why? Because I can, it's a simultaneous move game. So I can figure out what my profits would have been had I done something different. Okay. But the continuation values, I only know at the true M star. Okay. That's also true in the algorithmic pricing game. Okay. That's going to be the source of the extra, and I'm going to come back to this, but that's going to be the source of the extra multiplicity in experience-based equilibrium relative to Markov perfect Bayes. Okay. It's also the source of the supranormal profits that the algorithmic pricing literature says is collusion. It's just about the result of randomness and this condition. And I can show you that formally, but it's true. Just okay. It's not collusion. Okay, in any sense of the word. Okay. Okay, so that's the equilibrium notion. Okay, and so now I'm going to give you a algorithm, a learning algorithm, which will bring you to this equilibrium. Okay, that's the second part. Then I'm going to go to empirical work. The algorithm is a generalization of reinforcement learning or Q learning. So those guys from OR will know about this. Okay, in IO, the first time it's been used for a while in IO. It's iterative. So, and it's going to actually mimic an actual learning process. Okay. So if firms were actually learning in this way, okay, the firms could in principle learn in this way, okay? I'm going to show you there's problems with doing that, but they could in principle learn in this way. If you really did know that firms learn in this way, there's no need for an equilibrium assumption. Is that clear? Because I see how they're transiting, okay? It will pick out, the transition will pick out the equilibrium. It may pick out a distribution of equilibrium, but it'll pick out an equilibrium. And so you solve all the problems at once, okay? You solve the problem of multiplicity, okay? And you also understand the transition path, okay? Which is what you'd want to do, okay? So it's obvious then that there's problems with with what we do as a learning process, okay? Or I would be using it.
Solve them.
If you knew the primitives and you just made draws and you had a learning process, okay, the only way it would ever stop is at a Nash condition. Okay, that Nash condition would satisfy the equilibrium conditions.
So you're not imposing uniqueness, you're just saying that it doesn't matter.
Yeah, it will. Depending on the random draws, you could go to different equilibria. Okay, but you would get a distribution of equilibria. I've done this before.
Simple long enough.
Yeah, that's right. It's the long enough that's the problem. Okay. Okay. I'm going to also give you a direct method of computing equilibrium, which is much faster. And when we get to the empirical work. Okay. It's an iterative algorithm, just like all learning algorithms. Okay. So I have to start at some location, have some stuff in memory, update the stuff in memory, then start again, and just keeping on doing that time and again. Okay. So a location for me will be indexed by K. And it is, as you might have expected, it's just a vector of the information sets of the active agents. Okay. The objects in memory, I'm going to call memory MK, are these WK, these evaluations of the expected discounted value of future net cash flow, because that's what I'm going to need in order to make my decision. Okay. And HK, the number of visits to that location. Why the number of visits? The more times I visit a location, the more precise my estimator of the value of that location is. Okay, so I have to update LK, WK, and HK. Okay, so that's what I'm going to do. So look, I'm going to do what the OR guys call the greedy policy. So at iteration K, I have the W's for each of my possible M's at that place where I am in memory. I'm going to choose the M that maximizes my perceived expected discounted value. That's called the greedy policy. Okay. Then I'm going to take random draws on M star. I mean, M. So think of M as this is an investment game, this capital accumulation game. So M is a investment. There's a stochastic outcome from the investment. So I choose M star. With M star, I get a random draw from given my omega, I get a random draw in the increment conditional on M star. Okay. I update my location, my own location. Everybody updates their location. Okay. Based only on their information set. Okay. And I get a new location. Okay. So now how do I update perceptions? Okay. The simple, I'm going to assume that agents, so I implicitly assumed without telling you, I assumed agents, I know the profit function, and I know the distribution of outcomes. Okay, that's primitives. So what I can do is at iteration K plus 1, I can go backwards and ask myself the question, what in fact was the realization of what I did? Okay, so I got a particular profit. Whoops, this one. I got a particular profit and I went to a particular JIK plus 1. Okay, and I have a W in memory for that JIK plus 1. Is that clear? So I get a value for what I did that last period. Is that clear? Okay, that's like if this was the truth. Okay, that's a random draw from the expectation of what W is. Is that clear? So all that you do is you update the expectation of W with that random draw. Is that clear? Dates back to Robbins and Monroe. It's the oldest site you're going to see for a while. It's just updating like you update an average. You could update it just like you update an average. So how would you update an average? Up until this period, I had HK times hit this point, and now HK minus 1 point. So I take 1 over HK minus 1 HK, what I was before. Okay, and I update like an average. The way they write it in the OR literature is like this. This is the same thing. It's just a different way of writing. Let me say that's the wrong way to update. It satisfies the Robbins and Monroe conditions for stochastic integrals, but it's a stupid way to aggregate. And the reason it's a stupid way is because the draws that are farther in that you've gotten at later dates, they're more precise than the draws at the beginning. So you want to weight that accordingly. And if you were into this, you could get very complicated weighting. But the simplest thing to do is run a million draws and throw out, start again. And you'll start at a much better place. Okay. So properties, I've already said that. If you're at equilibrium, then the expectation of V star is equilibrium, and you don't move in expectation. Okay, that's what's keeping you inside. The algorithm has no cursive dimensionality. Eventually you wander into this subset of states R, okay? You don't have to learn anything for the whole huge state space. R does grow typically in IO problems linearly, but not exponentially like you do with state space. And the continuation values are just got by, so there are two problems, right, when you ask compute dynamic games. One is the size of the state space. You have to compute a policy for each point in the state space. That's the first thing. The second thing is you have to integrate out over all possible states in the future. Is that clear? Well, here you substitute adding two numbers together for integration. Okay? Okay, good. So the algorithm doesn't necessarily converge, except for when it's a zero-sum game. Then it has to converge. But there's a simple test for convergence, and it usually converges much quicker than other algorithms because it's smoothing it with the probabilities. Okay. Caveats. I already told you the first one. You shouldn't be using HKJ to thing. The big caveat is the algorithm takes a long time to converge. Okay. For major environmental changes, it's probably too long for an adequate approximation for firm behavior. On the algorithm pricing stuff, when we actually did calculations for a real firm, it took something like 5 years before you got to converge. There's no firm that's going to sit and let this program run unmonitored for 5 years. I mean, it just wouldn't do it, okay? It suggests the thing that's sort of interesting about it and what's missing from us is it suggests firms learn more from their own past outcomes more than from their own past outcomes at the state they were at. They're learning from something else, either other states that are close and that I don't know how to connect, okay, or from something else in the environment, okay, because they do learn and get to equilibrium. We've shown that. So finding a learning algorithm that's better than this one, okay, and adequately approximates behavior would be extremely useful. Okay, as both you get transition paths and you'd also select out the equilibria. So that's really a place for future research. Multiplicity. I already said Markov perfect Bayes is a special case of experience-based equilibria. It generates multiple equilibria. Okay, so we're going to generate even more. Okay, here's the source of the more. As I said before, there's a recurrent class of points. Okay, in this recurrent class, there's two types of points. There's interior points, and what's the definition of interior point is if I choose the optimal play, I stay in the recurrent class with probability 1. That's the definition of the recurrent class. But they're feasible things that could take you outside of the recurrent class. Is that clear? So if at this point, no matter what I take, which of my feasible actions I can take, okay, I stay in the recurrent class, I'm going to call that an interior point, and it has all the perceptions of the future correct. Okay? If, however, I'm at a point where if I take an M, which is not M star, I would go outside of the recurrent class, I haven't learned that that's correct. Is that clear? So, and moreover, okay, different perceptions of outside the recurrent class can give you different recurrent classes. Is that clear? Okay. So that's the extra notion of equilibrium. So we call them interior points ones that are right for every possible choice, and boundary points, points at which there are feasible strategies that lead outside of the recurrent class. Okay. Our conditions only ensure that perceptions outcome are consistent with the results from actual play at interior points. So, you know, perceptions of outcomes for some feasible but inoptimal policies aren't tied down by what you see in the data. Okay. So how do we deal with this? Okay. And now I'm coming into empirical work, so I have to do something. Okay. I can't just wave my hands and say theory. So one thing you could do, and we've done this a lot, knowledge of initial conditions helps mitigate the problem. Somehow, this is never, it seems so obvious to me. Only certain equilibria are consistent with historical conditions. You're starting somewhere. Is that clear? There may be millions of equilibria. So we did banks once, okay? And there are initial locations of the banks, you know, the bank's outlets. Is that clear? You know, that determines what the equilibrium can be once I change the counterfactual. Okay, it doesn't determine it uniquely, but it throws out almost a lot of stuff. So in empirical work, the way we tend to do this is we start where the data starts, the first period of the data. We change what we're going to do. Pierre and I are going to be doing direct-to-consumer advertising for pharmaceuticals. So we're going to start at the very first data point. And we're going to say, what we're going to do is we're going to say we're banning direct-to-consumer advertising. We're going to compute the equilibrium for banning direct-to-consumer advertising. Okay. And then we're going to run it through our data. And we're going to say, well, this is what would have happened had we banned direct consumer advertising. Because we see what happened, and this is what would have happened. Okay. That's sort of this way. And that's a useful technique, I think. The other thing you can do is, in this paper with John Asker, we provide a stronger notion of equilibrium in a test for it. It's just these boundary points, at least your actions at the boundary points are consistent with what you believe at those boundary points. So what you believe maybe come from, you know, getting into the recurrent class, or it may come from experimentation. Okay. And again, if you had a right learning model, there'd be none of these problems. So again, on the updating process, this is not in the paper, but this is just where, you know, sometimes the market environment suggests a learning process that can access more information that's just more efficient. So Hodgson, who's at Yale, he studies the drilling of oil wells. Okay, so I think it's in the British ones. Okay, the likely returns from drilling a particular well may be well approximated by the realized gains from nearby wells, and that's how he gets his learning process to be more efficient. Okay. If there are multiple disjoint markets, and one might use information from each market to update all markets, and that's particularly good when the same firms are operating in these different markets. So Jennifer Zhao is doing laying down lines for internet lines in different cities, and their same firms are acting in every different city, and they're doing overbuild of these things. So, and then the other place where this has been successfully used, I think, if the transport literature is the Brancaccio paper that was already discussed earlier. Okay, and other models in that transportation often use the value of past matches. So what you do is you say, okay, you know, I know how much it's worth to take my boat from here to Delhi. Okay, and match a Delhi with somebody. Okay, and why do I know that? Because there's an average of past times I've been at Delhi. Okay, and I can do so. That works very well for certain kinds of counterfactuals. Okay, if all one does is the shock to the profit function in the system, and there's no aggregate shocks. If there's an aggregate shock, it's a problem, because then the fixed point of this depends on where you are in the Markov process and where you were in the last periods before that. Okay, good. Okay, and then there's the non-stationary, which I'm not going to talk about. But maybe I should say a word. So the Markov transition, it doesn't bother me making this assumption. It's a good approximation to reality. It can be second or third order, I don't care. Okay, it just doesn't affect the math in any formal way. The non-stationarity does. Okay, so I've been assuming until now that the transition kernel, how I get from one point to the next point, okay, is stationary over time. Okay, so non-stationary can be built into the learning process, I should say, but you have to know more than that. Okay, so for example, sometimes you know the final state. You know, there's some state where everybody stops doing something. Okay. Another way of dealing with this is you might not know the final state, but you can use the expectation of the future by inverting the control at the last period, just like you do in BLT. Okay, I'm not going to go there. Okay, but it is possible to do that. Non-stationary is I think the serious problem with this stuff. Okay. Okay, so now I actually get to what I wanted to do in the first place, which is empirical work. Okay. The question that Pierre and I are asking is direct-to-consumer advertising of pharmaceuticals useful? So direct-to-consumer advertising of pharmaceuticals is only legal in 2 developed countries. These are patented pharmaceuticals. They only in 2 countries in the world, US, okay, and New Zealand. And in the US, it's a recent phenomenon. That is, before 1997, you could not advertise on TV, and now 85% of all the advertising is on TV. Okay, and it's been debated in the US, and it's still debated in the US. Okay, the arguments against having it on TV is there's incentives for excessive use. There's incentives for people to go to the doctor too many times, and there's incentive that because of detailing, which I'll come to in a second, there's incentives for the doctor to use it too much. Okay, and the returns are largely a result of business stealing. For many pharmaceuticals, you know, if you've got a particular disease, you know, we're going to do asthma, and we're going to do 4, and I'll get to them in a second. If you've got a particular disease, typically a doctor will tell you there's different classes of therapeutic classes for treating this disease. Within each therapeutic classes, there are a number of drugs. Okay, so if you go in and they give you something and it doesn't work, it really doesn't work, they'll move you to a different therapeutic class that might work. Okay, but if you go in and it works, but you get side effects, they'll move you to another drug within the therapeutic class typically. Okay, the drugs within the therapeutic class, you know, they have different release mechanisms, slightly different adhesives, things that can affect people. Okay, so the argument here is the returns, at least within the things within a therapeutic class, are just business stealing largely. Okay, it's not. There's no net benefit to society. It's just the direct. You know, you go to the doctor. Actually, the famous paper on this is "Ask Your Doctor." Okay, so you go to your doctor and you say, "I want Zantac or Accid." So you have heartburn, you want Accid. Okay, why? I saw it on TV, and TV said Accid's good. Okay, the doctor has to respond. Okay, the doctor will typically, and I actually, the way I know this is Al Ross. When Al was in Cambridge, I was having dinner at his house, and his neighbor was the head of MGH internal medicine. So I asked him, you know, if somebody comes in and says, you know, I want Accid. Will you give them Accid? Because there's no particular reason. Accid and Zantac and Pepcid, they all have about the same efficacy. And he said, what do you think? I'm stupid? I have 10 minutes with this guy. If he wants Accid and it's on the formulary, I'm not going to explain to him that Accid's the same as Pepcid. I'm going to give him Accid and get him out of my office. And, you know, it's got to be true. That's why they're spending all this money on this stuff. Okay. The arguments for, by the way, are that makes consumers aware that they can treat a condition before it can become serious. So historically, the big thing on this one was And this is, it was ulcers. Heartburn turns into ulcers if you don't treat it. The argument by the drug companies was, you know, you don't let us advertise. You know, people who don't go and see doctors regularly, okay, are not going to get acid or pen. They'll just live with the heartburn. Okay, these are typically poor people who eat very rich foods. Is that clear? If you actually let them advertise, they watch TV all the time. You let them advertise, they understand you can advertise that if you don't take acid, you're going to get sicker and sicker and eventually have ulcers. Ulcers is a serious disease. Okay, you're never going to be the same. You're in the hospital for treatment for your ulcers. It's okay. In truth, let me just say, ulcers has disappeared, virtually disappeared. So my parents' generation, I knew a lot of them that had ulcers. I don't know anybody who has ulcers now. You know, and it's because that they've been very effective with the drugs for ulcers. Okay, there are two kinds of ulcers, peptic and something else, but it doesn't matter. They've been good at both of them. So those are the arguments for and against. Okay. We also want to keep track of the impact of changing the counterfactual on profits. Okay. The reason we're interested in profits is because you know, calculations of the welfare impacts from R&D are huge. So it's probably the case, and I can't prove this, that $1 spent on R&D and drugs and pharmaceuticals, okay, is more socially welfare enhancing than $1 spent in any other industry in the United States. Okay. The numbers are huge because of the increase in the decrease in mortality and morbidity due to these things. We've made calculations. We're talking with trillions of dollars. So you do want to worry a little bit about profits. Okay. The other type of advertising is detailing. Okay. So DTC is direct to consumer advertising. Detailing is when they send an agent to the doctor to convince the doctor to use their pill. Okay. We're going to study 4 markets. Together, they're about 25% of DTC and 22% of detailing in the United States. These are the markets: anti-cholesterol, anti-asthma, anti-depression, anti-ulcer. A couple of things that you want to pay attention to in this, reason I show this is, this is the average expenditure on detailing among the drugs in the anti-cholesterol market. Okay, this is the average expenditure of the top 4. Okay, similarly, this is the average expenditure of DTC, and this is the average expenditure of the top 4. These are markets where the expenditure on DTC and detailing are highly concentrated in the top firms, in the top drugs. Okay, that's the first thing. It's also the case that, by the way, relatedly, it's also the case that the industries, the markets with a large amount of detailing are the industries with a large amount of DTC. The rank correlation is 1. Okay. That's true also within markets. So this is just the plot of actual, just data. Okay. So it's actual DTC on the x-axis and actual detailing on the y-axis. And the colors represent the different industries, because now we want to look at within industry thing. And you can see it's highly correlated. This is the probability. This here are our kernel estimates of the probability of 0 DTC given detailing. Okay, so this is all just data. There's nothing else going on. And again, there are 4 different industries: ulcers, antidepressant, anti-cholesterol, and anti-asthma. Okay, so now I'm going to try and analyze this data and show you what it is. And the truth, I'm not going to get to the end, so we're not finished yet. So you're going to have to live with me a little bit. I mean, that's been true of almost every paper given here this time, but equally true here. I don't feel so bad. I'm going to use 2 different models. Okay, remember, the theory just told me, if I know what's in the information set, I know what to do. Okay, but I have to find out what's in the information set. Okay, So there's going to be, I'm going to have an empirical model, and the empirical model, it's not going to impose the equilibrium conditions. It is going to impose that the agents are their perceptions, they're maximizing given their perceptions, but the perceptions need not be correct. Okay, or they need not be equilibrium, whatever you want to say. Okay. And then after I do that, I'm going to move to an equilibrium model, which imposes the constraints of the EB. Okay. So what does the empirical model do? It determines the state variables. The state variables are going to condition on two things. They're going to condition on variables in the data that I can see that advertising responds to. I can regress advertising on stuff, and I can see what it responds to. Okay. And so, but there are things that are not in the data, is that clear? That the advertising is responding to. That's the error in the regression equation. So I'm going to let that be serially correlated. Okay, like all economic variables, just about. And I'm going to have to find out what are the properties of those unobservables. And then I have to determine the features of the data that need to be replicated in order to get an adequate approximation of behavior. You'll see what they are in a second. So the empirical model is in some ways similar to the stuff that was done before. Yesterday, they talked about by Ariel Benkard's other work, this work by us. There's two differences. One, I'm not going to assume equilibrium perceptions, and all the rest of the empirical work assumed equilibrium perceptions. Okay. Two, I'm going to allow for a serially correlated unobserved state variable, and none of the other empirical work allowed for that. Okay, none of the other stuff that's on a dynamic game, that's a real long fit. Okay. So then I go to the equilibrium model. I'm going to introduce an algorithm for computing equilibrium, which doesn't have low computational burden. I'm probably just going to give you an outline of it without giving you details. But I'm going to compute equilibrium for the in-sample period. So with DTC on, I'm going to compute what equilibrium looks like. And I'm going to compare it to the empirical model and to the data. Okay. Then I'm going to compute an EB for the counterfactual world where DTC is banned. Okay. Actually, we want to do two counterfactuals. And we haven't finished the first one yet, but might as well tell you what the second one is. The second one is what we want to do is we want to ban direct. We want the FDA to do the direct-to-consumer advertising. Okay, and they do this without using the name of the drug. It just says, if you have heartburn, okay, you should go see your doctor. The doctor can give you a pill, okay, which will solve your heartburn problem. Moreover, if you don't do this, you're likely to get ulcers and you're going to be in the hospital the next quite a lot of time. But it doesn't use a brand name. Okay, and then it taxes the sales of these things to make up for the FDA costs. Okay. So we haven't done the first one. We certainly haven't done the second one. But it's sort of nice to think of where we're going. Okay. What effects of DTC are we interested in? Why am I doing all this? Okay, or why are we doing all this? Much of the prior empirical literature, actually all of it that I know of on this topic and probably on most other topics, is what I call unilateral effects. What it does is it says, it uses some source of exogenous variation, presidential elections for costs for the price of the advertising, borders of the DMAs where they advertise, to see what would happen if one of the firms or the firms on the border or at one small period stopped advertising. They'd get a causal effect that was that. Okay. We're fundamentally interested in equilibrium effects when everybody changes. Okay. And the fact that you change and something goes wrong and I don't change is very different from the equilibrium effect when we all change. Okay. And especially on something like advertising. Okay. So that's one thing. Again, DCC induces doctor visits where patients request a particular drug, hoping the doctor or formulary are compliant, that they do what they're asked. So this suggests you can't, if it's true, okay, it suggests that detailing will respond to a lack of DTC. And there's a question of how that would affect the results. So if I can't just kill DTC, I have to see the response of detailing to that, okay? Because it's an equilibrium response, okay? And if I'm going to stop all DTC, I'm going to change the incentives to do detailing. They're related, okay? Both DTC and detailing are dominated by the highest selling firms. Would banning DTC change market structure? Okay, that's another typical IO question, okay? Are we going to get smaller firms or larger? What's going to happen? Finally, how would banning DTC impact profits and how the incentives to do R&D? Those are the kind of questions we're interested in. Okay. So let me say there's good a priori reason to believe, and I'm not going to, unfortunately, I don't really have answers on this yet. I mean, I do have answers, but I'm afraid to tell you what they are because they aren't robust yet. So I don't want to tell you what they are. But is DTC particularly impactful in markets? You would think DTC would be impactful in markets where the usefulness of the medication is least self-evident. You wouldn't know you need a drug unless you watch TV, okay? So for cholesterol, you know, the only way you really know you need cholesterol is you go to your doctor, you ask him for a test, he gives you a lipid test, and he tells you whether you need a statin. You know, that's the way you find out, okay? Similarly, for depression, if you read the literature, and I've just read little bits, lack of mental health awareness is really a major reason for depressed people not seeking help. So you might think that direct-to-consumer advertising was more important in these markets. Right? And in fact, so far it comes out that way, but I don't want to get into it yet, okay? Asthma, on the other hand, you seek help for asthma because you wake up in the morning and you can't breathe. You have very bad breathing problems, okay? If you have asthma, you know you have a problem and have to see the doctor. It's to a lesser extent also true in ulcers. You actually, you can't, you can't digest. And eventually, if it gets to ulcers, you really can't digest, and you really have to go to a hospital. So I'm not going to provide detailed numerical results on counterfactuals because Pierre and I are worried about robustness. We can get slightly different answers from different ways of doing things. What I will do is provide some pictures for you to give you some idea of what's going on in the answers, okay? Okay, so remember the first lecture which told you about demand systems and cost systems and stuff. So I got to do that in order to go further, okay? So the data has 38 periods of quarterly data for each market. So there's these 4 markets. There's 38 periods of quarterly data. I'll show you what it looks like. So we're going to do a BLP estimation on each market. Let me just say, the only thing you really need to know about BLP is we're going to load it with all the X's we can, okay? So, okay, and random coefficients on price and stuff, and molecular effect. And then in addition to that, what BLP does, and the reason it's useful for aggregate studies like this, okay, is it makes sure that there's an unobservable Xi, okay, which you've heard about before today, which ensures with probability 1 that you get market shares exactly correctly. That's why people use BLP with aggregate data, okay? Because at least you're going to get demand right. You're ensuring that by the way you do it, okay? So that's what we're going to do. And then that residual, the Xi, that we get out of it that makes it fit, that isn't, after you put in all the X's, we're going to say that evolves like a Markov process. Okay, so CT is a function of CT minus 1, and the advertising in the interim. Okay, so that's one of the things that moves this quality variable. Okay, so we put in as many observables as possible. There were 20 to 46 parameters depending on the market. Okay, there were price interactions, molecule effects, all sorts of things. This is what it looked like. You can see the number of products are large, larger than you're used to seeing in these studies, but they're in different ATC4 classes. ATC4 classes are therapeutic classes. So as I was explaining before, there are these different therapeutic classes for each disease. Okay, So I'm going to come back to that, but you might think that the within class competition is stronger than the outside class competition, okay? So that's the number of observations. There's nothing special about this. These are the kernel density estimates of the residuals of the quality terms, which look fairly normal, and we're gonna assume normality from now on, okay? Okay. So then the next question is, how does this C evolve? Where does advertising end? Okay. So we're gonna say CT is a function of CT minus 1, but the increment in CT over CT minus 1 depends on stuff, which most of it comes out to be 0, by the way, plus a function of the two kinds of advertising. Cap D is DTC, is direct-to-consumer advertising. Little d is detailing, okay? So it's this function that's going to drive much of what we're doing. So let me go a little bit into this function. We're going to write it. C enters the BLP demand system as an exponent. Okay, so you want something in logs to take it. Okay, so we're going to say this increment is a function of detailing and a function of DTC, and perhaps a function of the cross product between them. The cross product function is important, and the reason it's important is the following. Just from the structure of the functional forms in BLP, you can believe me about this. Okay, if this wasn't, whoops, let me go back. If this wasn't negative, you're gonna by assumption you're going to assume that detailing and DTC is complements. That is, if I increase DTC, the marginal product of detailing goes up globally. Is that clear? It's only if this is negative can that be reversed. Okay, so we didn't want to set it. We wanted to let the data set it. Okay. So I'll show you the answers now. So this is the regressions. The one in blue is the ones we're going to use. Because if you look at this is the cross product term. Okay. And you can see it's near 0 in every market. Only once it's just barely significant here. So we're going to just go with it 0. Okay. The other thing you should note about this is there's a very high serial correlation in the, whoops, got to go the other way. There's a high serial correlation in the row, okay. It's between 0.93 and 0.97, but you should remember this is quarterly data. So you're used to thinking of annual data, and if it was annual, it would be somewhere between 0.75 and 0.89 per annum, but that's still very large. Okay, that's large enough. You got to keep track of it.
The little eights, there are a lot of zeros.
Yeah, I'm going to come to that. That's why when I said you got to reproduce the data, that's one of the things you have to reproduce. Okay, so actually I'm giving you the end result, but we did a lot of testing of this equation. Okay, analytic framework. How am I going to get the model? Okay, so I'm going to let A be the vector of the couple of detailing and DTC. Okay, so I have a perception of the expected discounted value. In order to make my decision, I need a perception of the expected discounted value given my information, the public information and the private information. Okay, I'm going to keep track. J includes all public and private information, which includes this C from the thing, but I want to keep it separate because we're analyzing it separately. So what is that? The script D again is my perceived expectation. It need not be correct, okay? But it's what I'm going to try and maximize on the basis of, okay? And it's just the discounted value of future net cash flow, okay? So E is the agent's expectation operator. JT is a set of variables the firm conditions on when it making its advertising decisions. And that's going to include observables that are in my data. different ones for detailing a DTC, okay? And a serially correlated unobservable for each. That's what's different from before. Yeah. You're going to see they're important. So what do? You look at this and you take the first order condition with respect to advertising, and you get that is the marginal benefit of the last unit of advertising. If advertising is positive, that equals the dollar of advertising. Okay. If that is not positive, you get a 0 and you shut down. Okay. So it's Kuhn-Tucker conditions. Let me say there is shutdown in the data. I'm not going to show it to you, but there's a lot of it. I'm not showing you a lot of stuff. Maybe I'm not showing you enough stuff. I might be finished early. You see in many data sets on advertising, by the way, and pricing, you see big changes in advertising. But this is not like what you see in sales at grocery stores. It's not like, there's two prices, a sales price and a not sales price. You see it in all these drugstores and it goes up and down, like that. This is what happens is these guys, they stop advertising. And if they stop advertising, they stop for a while. Okay, for a fairly long period. The data shows you, the paper shows you how long. Okay, and then something happens and they restart. Okay, okay. Okay, I sort of skipped things, so let me go back. Okay, so how am I going to operationalize that expectation? Okay, what I'm going to say is, look, what does the guy know? Okay, I'm going to assume that the agent making these decisions knows how advertising affects quality, at least on average. There's an increment that is random, and it knows the effect of quality on profits. Okay, so that's going to be, so one term in this is the expected value of the derivative of profits with respect to advertising. Okay. Actually, there should be a log here. I don't know why it's not there. Okay. And then so those things he could learn himself by just looking at what goes on. On the other hand, the actual future returns depends on what his competitors are going to do. He knows that the competitors have different things, and there's a question of how he's going to take account of that. Okay, so what we're going to do is we're going to say, look, I'm going to find out from the data what advertising depends upon. Okay, so that's going to be my W's. Those are observables. And then there's going to be just serially correlated unobservable. So they're observables, and then I'm going to put in a serially correlated unobservable for each one. And I'm going to assume the serially correlated unobservable is Markov. Okay, so that's essentially the model. Okay. So let me just say, the first thing we did is we went to the data and we did, within and between, okay, for each firm on what advertising responds to. Okay. And, this was one of the more instructive empirical things we did, okay, because it came back and it said, well, the thing that it responds to the most is the derivative of current profits with respect to advertising, or log profits with respect to advertising. That makes so much sense. Trying to compute the value function is just impossible. It's what started all this, okay? But the value function is just an iterative of the profit function, right? It's profits today and then profits tomorrow, and it's highly serially correlated. Okay, so using current profits as a proxy for the value function makes a lot of sense. Okay, the other things that come on all the time is time to loss of patent exclusivity. As you approach the end of the patent life, you stop doing advertising. Okay, there is a little bit of advertising after patent excludes, but not much, and certainly not much DTC. A little bit of detailing stuff. Okay, and then the third thing is the advertising competitors. So this enters in two ways. The advertising competitors affects the sea of competitors, and therefore it affects your market share. Is that clear? Just from the demand function. Okay, so the demand function will ensure that the advertising of competitors has a negative effect on you. In addition, we found that the advertising of the competitors in the same therapeutic class had an additional effect. Okay, so that's in those ATC4 classes. And then separate observables for detailing and DCC, both highly serial correlated. Okay. So now I get to data issues. So I now come. Okay. So there are a couple of things I need to, do that we often have to do in IO. One is we don't observe marginal costs. Okay, this is one of the things that is a problem in much of IO because cost data is typically proprietary and demand data is not. Okay, so the typical thing you do is you take the first order condition. We have the demand function. Okay, so the first order condition, the marginal cost. First order condition for price is it's a function of cost. Okay, so you use the actual price, you back out, we have the demand system, you back out costs. Okay, that's what's standard in IO now. Okay, there's another way of doing it. That's the Nash pricing first order condition. There's another way of doing it, which is saying, look, I can look at the dynamic equation for advertising, the amount of profits I get for the marginal unit of advertising. Okay, I just integrate out over the future. Okay, what profits I would get. There's going to be a cost that makes that actually equal to 0 on average for each drug. Is that clear? And that's another way to back out the marginal cost. It doesn't require a pricing equation. All it requires is the advertising equation we need anyway. Okay. Okay. So that's one thing I got to do. The second thing we have to do is as what you just asked, okay? Firms stop advertising for a sequence of periods, but then restart, okay? So just like traditional, if we didn't correct for this, we'd have a selection problem. They stop advertising when their omega is very low, okay? So, so that's going to be so it ends up being correlated with the x's in the equation, okay? Moreover, if we didn't do a correction for that, we couldn't really compare the data to our models, okay? Because in the data, there is this zeros, okay? And we want to be able to do that, okay? Okay, so I refrain from doing much technical stuff in this lecture. I figure after 2 days, maybe there's too much. Okay, okay. So how do I estimate this? And I'm just going to tell you words, okay? I'm going to set the dynamic equation for first order condition equal to $1 for average for each type of advertising equal to $1. That gives me the typical Kuhn-Tucker condition. I'm either at a corner and spending anything makes me go down, okay, or an interior maximum, okay, at an optimal point. Okay. So then I get the log derivative of profits on the right-hand side, and in that log, there's a log derivative profits, there's time to patent exploration, there's advertising of my competitors, and there's an error. And we know that error is serially correlated. Okay, seeing it's serially correlated, it's going to be correlated with the profits from last period on the right-hand side. Okay, so we do what's called quasi-first differencing. I don't know, does everybody understand what that is? You take advertising minus the row from the serial correlation minus row advertising t minus 1, okay? And you figure out xt minus row, xt minus 1. And then on the right-hand side, the error is the innovation in advertising, which isn't correlated with the past, okay? So that's how we get around that problem. Then we do a correction for selection. We already have these quasi-first differences. So the correction for selection is just on these innovations, and we use normality to do that. Okay. And those who know econometrics will understand that, and those who don't have a chance if I explain it anyway. So in 10 minutes, okay. So you might as well. Okay. The estimation algorithm. It's a nested estimation algorithm. As I was saying before, for each theta, I can find the Cj for that molecule, given that theta, which just makes the average of the dynamic first order conditions for each product equal to 0. Okay, not each one, but just the average. I have 38 periods of data for this guy. I can make the average go to 0. Okay, I'll choose the C for that molecule so that that average is 0. Okay, so that's going to give me 87 parameters for that theta. And then I'm going to maximize over theta. I'm going to use a typical Euclidean norm to maximize over theta. Okay. Or I actually Pierre did most of this, so it's not I. I'm going to show you. So we did this 2 ways for the pricing for the cost variable. One way we did it is we did the NASH. We wanted to compare this, the NASH, to the dynamic one. Okay. So this is the price first order condition and the advertising first order condition. These are margins. So it's price minus cost divided by price. So what's the margin? And you can see for the advertising equation, it's pretty much, it's about 0.8 is the margin. Remember, this is an industry where most of the costs are sunk. Okay, this is what's expensive is the R&D and getting it through the FDA trials. Okay, that's what's expensive in this industry. So this is not unexpected. When you do the price first order condition, however, you get much lower numbers. Moreover, to check whether we were nuts or whether there was something wrong with the price first order condition, we did also for generics using the price first order condition. Is that clear? Generics don't advertise really. There's a little bit of advertising, but very small amount. You can't estimate the dynamic equation for advertising for generic, but you cannot estimate the price first order condition for generics because they are in the market and they have a price. Okay, it worked out that for all of them, oops, how did I get there? I should be going up or going down. No, up. For all of them, the generic markups were higher than the markups for the at least on average for each market. Okay, the generic markups were higher than the patented markups, which we just didn't believe. Nobody in the industry believes it. Okay, so there's something wrong with price first order condition. Okay, this goes back to the first lecture I gave, which I said, we do very well on price first order conditions on well-defined static markets. Okay, you start getting dynamics or you get to bargaining and you do very poorly, or you don't. Let me put it differently. We don't really know. Okay, one way or the other. This is unfortunate for us. Okay, why is it unfortunate for us? Because we're going to do a counterfactual. Okay, if we change advertising, we expect prices to change in the counterfactual. Okay, and we don't know, we don't have a model for the price change. Is that clear? And that's the same problem I alluded to in the first lecture. Okay, knowing more about how prices react in non-standard markets, non-standard meaning non-retail static markets, okay, would be very useful in IO. I can tell you what we're thinking of doing, but I don't really have an answer to this. Okay, theta. So there's the 87 cost parameters. I just gave you summary statistics on this, and then there's 12 other parameters, the demand system for each drug. So 48 more parameters. And it looked very much like the reduced form, so derivative log profits was positive and significant everywhere. So there's 2 of these equations for each market, right? There's a detailing equation and a DTC equation for each market. Okay. Time to patent expiration was always positive and sometimes significant, sometimes not significant. Once you do all these corrections, the significance goes down, okay? Because you're only looking at the increments rule and all of that, okay? And advertising to others in the same ATC4 was -1 significant, okay? So among all of this, the only thing we're going to really use, other than the fact that these are the variables and this is the way we're going to correct for selection, is the disturbance process we estimate. Because we don't know what the disturbance process will be in a counterfactual world. Is that clear? So, I mean, it's okay when we're comparing to data, okay, the empirical model or to data, but in the counterfactual world, we're making an assumption, okay, that the disturbance, because we don't see what anything. So The disturbance process, again, very highly serially correlated, 0.91 to 0.98, but these, again, quarterly data. So per annum is between 0.7 and 0.9, but that's nothing you can ignore, okay? It's not. In all the detailing, it was like that. In DTC, in 2 of the 4 DTC equations, it was like that. In asthma, it was lower. And in ulcers, it was lower yet, okay? But what happened in ulcers, it was just dominated by a downward trend. This is, what's going on in ulcers is they're all going down, okay? And yeah.
What you refer to
It's, wait a minute. Yeah, I can do this. Well, it's this omega from the advertising. The advertising equation, my perception of what my competitors, how my competitor has got an error in it. And that's what it is. Okay, so that's correlation. This is the fit. Okay, so on the x-axis is our prediction, and on the y-axis is the data. Okay, there are 2 things about this. The top 2, one is detailing, which is on the left. It's the one with lots of data. And one was DTC. DTC has about 1/5 the data. There's a lot of patents that do detailing, but no DTC. Okay. The top ones, you got to expect this to work, okay? Because it's just using last year to predict this year, because omega t minus 1, and okay, so you got to expect it to work. The only thing that's really telling in this picture is that it should be distributed about this line with a 0, mean 0. That's what the assumption is. And it's pretty close to mean 0. I mean, this is different. The bottom is sort of more telling. Because what we do in the bottom is we say, okay, let's start at the very first period. We have 38 periods. We use the empirical model to predict the next period. And then with using the next period's prediction, we predict the second period. And from using the second period prediction, we use the third period and so on. Okay. So we do that for 38 periods. And this is what you get. It's still not too bad. It's not great. It's certainly better for detailing than for DTC, but it's not bad. For predicting 38 periods out, I don't know. You decide whether it's good or bad. But that's what it is. Okay. Okay, so that's the empirical model, and that's the fit of the empirical model. Now I got to go to equilibrium. Okay. So as I said before, there are 2 problems in computing fixed points for dynamic games. One is just the amount of state space, the dimension of the state space. There's a lot of there's a lot of variables. If you have 20 variables, in this case, we have like for 8 variables per market. And and if each firm had 8 variables, it would be 8. And if you divide it into 20 slots, it would be 8 to the 20. Okay, that's a number that's too large if we did it that way. Okay. So that's one. And the other one is the integral over the future, which is, okay. So how are we going to get around this? I'm not going to compute policies for all possible states. We're just not going to do that. I'm only going to compute separate policies for each product in each time period. Okay. That's a small number of policies. We have 40 products. Okay. 40 time periods. That's 1,600. That's a whole lot less than 10 to the 20, whatever it is. Okay. Moreover, there's no discretization or approximation in this. Okay, it's just important. But what I'm suffering from this is, okay, I'm assuming they're in equilibrium all the time when I do the calculation. Okay, that's why I'm able to do it. Okay, I never compute points that aren't touched on in equilibrium. Okay. Okay. And then the continuation value is just, we do what we did before in the learning algorithm, but slightly differently. We just simulate the future values. So I have the model parameters. Okay, I have a set of parameters. So I know advertising in both things. I know the profit function. using those parameters, okay, I simulate for this firm and then for all the other firms, this period. I find out where they go to the next period. I take the advertising at the next period for each one of these guys. And I go again, another period. Okay, and I do this 100 periods out. Okay, I do this 100 times an average because it's the expectation of the future that has to be right. Is that clear? So then I get an answer, okay, for what the policies are, what the expected discounted value from these policies are, okay? The expected discounted value I calculate won't be right unless the policies are right in equilibrium. So I use the expected discounted values to update the policies in an iterative thing. Again, I do it again. I keep doing that until I get to a fixed point. Okay. So to show you that on the algebra on the table would take me 15 minutes, okay? But this is the idea, okay? And it works with some trepidation, but
I'm not sure if there's an easy answer for this or an answer at all. Maybe there's an easy one, which is probably wrong. But do you think data on perceptions of firms about, say, revenues and inputs of the type that, say, you know, MOBS or the managing expectation survey collects here would be useful in helping this? Because you're getting a IE, for example, out of that.
we don't have, but let me just say, I actually think expectations data, if we have good quality expectations data, it's got to be helpful for all investment decisions. That's, I don't know that we have good quality expectations data, okay? But if we had it, because that's what's driving people's incentives to invest in any kind of investment, okay? So, okay. So now I'm going to give you some more pictures, okay? And I will finish a little bit of it before time. First, the EBE versus the empirical model and the EBE versus data. Okay, so now I'm going to, okay, so this is detailing. On the right-hand side is the data and the experience-based equilibrium. Okay. On the left-hand side is experience-based equilibria versus the empirical model. Is that clear? So it's pretty clear that we don't get it exactly right. The experience-based equilibrium, the empirical model is not replicating the equilibria exactly right. I don't, you can decide for yourself how close you think that is, okay? It's probably less close than it looks because these are in logs, but it's pretty close. And then if you look at the fit with the data, it's actually, I could go back, but it looks about the same as the fit of the empirical model with the data. It's not much different.
Just 0.69.
Yeah, this is actually a little bit worse.
Yeah.
Okay, it is a little bit worse. The empirical model fits the data slightly better than the experience-based equilibrium. Okay. Here's the same picture for direct-to-consumer advertising. Again, on the left is comparing to the empirical model. You can see there's much less data. And on the right, there's a comparison to the data, the experience-based equilibrium in the data. So actually, the experience-based equilibrium does a little bit better with DTC, and the empirical model does a little bit better with detailing. That makes some sense. There's 1/5 the data with DTC. So it's telling you there isn't that much data. When there isn't that much data, the structure helps, okay? When there's a lot of data, you want to trust that. That's sort of what it's telling you, but I think it does make some sense. This is density, the density of log detailing and log detailing and log DTC with both the data. So EBE is red and blue is the data. And one of these is DTC, and one of these is detailing. I guess the bottom one, I'm missing the, so you can see, you might expect this. First of all, it's sort of interesting that we fit the zeros so well. Okay, I mean, these are just kernels. We get the numbers, then we run a kernel on it. And this is a kernel from the experience-based equilibrium for the probability. And this is the kernel from the data for that probability. Okay, it's pretty good. But as you might expect, you know, we have much more structure in our than is in the data. We have a very high correlation between DTC and detailing. Okay. So again, I'm now going to go to the counterfactuals. I'm not really going to tell you about the counterfactuals. I'm just going to sort of give you an impression of them. Okay. So some caveats. Both equilibrium calculations that with and without DTC are going to assume an equilibrium. Okay, so I'm assuming that from the day I started, okay, for, you know, when I do an equilibrium with DTC, and I do an equilibrium without DTC, they're all in equilibrium from day one. Okay, and then I'm going to compare to the data with DTC in equilibrium and the data without DTC in equilibrium. Okay, that's the exercise. Okay. I cannot do anything for the unobservable processes except for what's in the data. Okay, because I don't see anything. Okay. Both equilibria are selected. Okay. I use the firm state in the initial period to select. Okay. And I also make sure they're boundary consistent, or we make sure they're boundary consistent. Caveats we're working on. Okay. We know there's a problem in the equilibrium program. So I'm going to tell you things that came out of all of them, and we're in the middle of fixing it. Okay, we think we know it's wrong. So I'm just going to give you general results, okay, instead of details, so I don't feel guilty afterwards. But even once we give you these general results, we have to have them all. We don't have them all for how pricing is going to respond to no DTC. Is that because we know the pricing model from that IO typically uses is wrong. So we were going to do a bunch of, by the way, we're going to do a bunch, just 2 or 3 different things and see if it mattered. Okay. By the way, I don't know how many of you know micro-BLP, the paper in the JPE. So when they do counterfactual, they do exactly what I was saying because we couldn't do it any other way. But nobody pays attention to this. But in micro-BLP, when we predict what would happen if Pontiac got thrown out of the thing, and if we added a car, which was a SUV that was high-end, that's how we get prices. We just regress it on C and other stuff, and we got the prices. So we're not the first to run into this problem. So here's the major effects that seem to come through all of our stuff, okay? First of all, the share of the largest selling products fall markedly in all markets. And so the measure of these markets are going to become less concentrated. It's the fact that they're doing DTC and a lot of detailing with it, okay, that's getting these, pepsid and axid way up there in the cholesterol thing. Is that clear? And the same with other ones. And when you take away that advantage, typically what happens is the big selling firms decrease their detailing as well as their DTC because they're strategic complements, okay? And they become much smaller firms, much smaller products, okay? Detailing falls when we ban DTC in all markets, okay? The question is only really the extent to which they fall. And, there's this cholesterol and, there's these differences between the market. And that's where we've gotten different answers depending on how we did it. And I don't want to tell you. Profits of branded products fall. Mostly the fall is among the top big firms, okay? But the fall is much smaller than the unilateral effects estimated previously. So, there are 2 papers out there. They're actually really good papers. One by the guy in Chicago, Shapiro, and one by Stark and Singleton. They both use, you would believe the variation they're using. One is on the DMAs and one is on the costs of advertising and stuff like that. They get much larger effect. They get much larger effects than we get. The funny thing is the profits of generics actually rise. That could have went either way, right? Because the fact that we're advertising for branded drugs can tell the guy, well, you need a drug. He goes and the doctor says, well, maybe you should take a generic, which is 1/10 the price, okay? But that doesn't have so that there may be a positive externality like that, but it's far outweighed by the fact that once there's no DTC, people start buying more generics instead of the Pepsid and Max and stuff like that. The thing you got to remember about this is it's the branded products who do all the R&D in this industry. So if you cut you might think it's a good thing that the branded products and the big branded products go down in price, but you're going to lose R&D incentives. Okay. And particularly right now, after what's going on in the United States. So I don't know how many of you read the newspaper, but Trump has claimed that he's going to force the drug companies to charge like you guys charge, the UK and Europe and the rest of the world. Okay, so I can tell, Kate and I have a paper in the Preceding National Academy. If you did this, if you made all the developed countries in the world, everybody with more than $50,000 per capita income, harmonize drug prices, okay, and then make sure there was enough profits that there are today, so the R&D incentives don't change, okay, and ask what happens to every country's drug price. Your drug prices, for every dollar that you now spend, you would spend $2.85 if this was harmonized. The United States would spend 50 cents for every dollar. Is that clear? The problem with this, from the point of view of society, is you kill that, you also kill R&D incentives. And the R&D incentives, we make the calculation in this paper, they're just an order of magnitude more than the cost of the R&D. They're just not, because the R&D incentives, what we calculated, okay, is we gave $100,000 per life year, which is cheap in this game, and $50,000 per year of no morbidity, and no morbidity over the age of 65. No morbidity in this, it's not morbidity like you think of it. It's like you can't feed yourself, or you can't, because they have surveys of this. Okay. And if you do that, it comes out to something like $4 trillion per decade, which is over 5 times the cost of R&D. And that includes, by the way, private and public expenditures on health R&D. Okay. So it's really a mistake. This is just from drugs, not from any other part of the health network. Okay. So mortality in a generation, in the 10 years, last couple of decades, just because of drugs, you've increased our lifespan by about 0.4 to 0.5 years per decade. And if you figure out the value of that, when you start multiplying it by 300 million people, that's just the US value. That's not, and by the way, you guys use the drugs. The same drugs we develop, you use. I'm not even counting that. Okay, I don't read, because I was trying to convince Trump, not you guys. That. So it's a huge amount. It's really a mistake to kill the R&D in pharmaceuticals. Lars?
Yes.
The patent expiration is, you get to a patent expiration date. That's a good question. We fixed that. Okay. We stop all advertising after the patent expired. And that's more or less what happens in the data. And we did that even for the counterfactual, where we have these models which would predict positive advertising. So there are 2 ways to handle it. So that's a good question. So we only see 38 periods, right? And there's future. Okay. So there's 2 ways to do that. One is to simulate out 300 periods, whatever. The other way to do it is you can show that if you invert the advertising in the last period, it gives you the expectation of the future derivative. Okay. And so use that for the future. And the advantage of that is you're not assuming the stationarity and everything else that's in sample for the future period. Whatever the firm thought at that period, we use it. We've done it both ways, by the way. But currently we're using what I just told you. Any other questions? Well, I think, let me say, and this may be my last slide. I don't want to show you this, but that is one of the differences. So I guess this is my last slide. That's all I have for now. Thanks to the UCL Economics Group for reminding me, and thanks for all you guys sticking around until 7:30 at night to listen to me.